Good evening, everybody. This is the lecture named after me for some reason that I don't completely understand. I'm Richard Weinstein. I'm Professor Emeritus of this hallowed place. And the lecture that is called the Weinstein Lecture is supposed to be a way of bringing people who have important things to say for architects, but who are not themselves part of the architecture culture. And that certainly is true tonight, although, as you will see, a lot of the work could have been done by an architect, even though it's been done by a climate engineer. Over the last weekend, news began to surface about Google's browsing outside its job description. Not automatic cars or weird glasses, but into our territory, construction. Big buildings, big budgets, big infrastructure, and big, even huge environmental impacts, as much as 50% of the world's carbon footprint. Frank Gehry has already spun off Gehry Technologies, which is now bigger than his architectural office, and is based on software initially developed to construct Bilbao, but now controls the same aspects of the building process that interest our pushy Silicon friend. The Google motto is "do no evil," and being true to themselves, they claim to be able to cut construction time in half, save a universe of energy, and thus become the Greek god. In doing no evil, they estimate a profit to the company of $120 billion annually. They think they found a way to control the construction process using computer software. $120 billion annually. A lot of what they seem up to sounds like Gehry Technologies, but what matters for our purpose is the Google-ish emphasis on the environment and the digital domain they both play in. Most who are knowledgeable regard the future climate of the planet to depend mostly on China and India because of the size and growth of populations that will be moving to new or expanded urban settings. This means huge investments in buildings and infrastructure with monstrous, big-footed carbon imprints in the snow, if there is any left. How else to face Bigfoot, except with the latest technological weapons we all look for and look at? Will it give us the power to limit growth by saving energy, by managing the whole construction process, from the extraction of raw materials, the energy cost of their manufacture and transportation, of construction, operation, and maintenance, the price of offsetting environmental impacts, all the way to demolition and recycling? For this to occur, we will need comprehensive software to read out the costs and benefits of interrelated choices, including design choices. As climate change disasters continue to degrade our earthly home and collective suffering increases, political pressures will become unmanageable. The bloody troubles in Egypt are the result of rising bread prices and near starvation brought on by drought-driven wheat shortages. Less is more sea. These pressures will eventually result in regulatory limits within which architects will have to improvise by the numbers, with design consequences we cannot yet completely understand. The climate engineer will be ascended as a master of the regulatory bead game and have more to say about the way buildings will look, and some already look the better for it. This is especially the case when Transsolar is involved, to reawaken our pleasure as designers in finding form generated by truths of new technology, not to mention the implied benefits of survival. Transsolar has the confidence of our finest architects, not only because of their triumph over facts, but because their technological mastery is driven both by aesthetics and by an evident sympathy for nature, with the sun at its center. Thomas Auer.
Richard. Yeah, thank you for the introduction. I'm really very excited to be here today. It's a great honor, I have to say. Talking at UCLA, but also being here in Los Angeles. I'd love to come to Los Angeles for various reasons. You talked about climate engineering and let's say, the environmental impact building construction has, and I think it's a variation. Yeah. This works better, much better. Yeah, there's this question on global warming, and I think buildings are responsible for something like 40 to 50% of all carbon emissions worldwide, and there's this ongoing question whether there is something like global warming. I think what we saw recently, not just what just happened, but over the course of the past, let's say, decades, I think there is sufficient evidence, and for the last ones who do not believe in global warming, I brought this one. So I think that's the last proof. When I showed this in Italy, actually, the question was, how does 2020 look like? A question I haven't expected. So just briefly about Transsolar, like Richard said, most or more than I can tell you about Transsolar. I think we are a very small firm. We are an engineering firm. We do climate engineering. We have something like 50-ish people sitting in 4 offices. Our main office is in Stuttgart. This is the TV tower from Stuttgart. And we have an office in Munich, in New York, and just opened an office in Paris as well. Everything fairly small, and I think I don't need to mention that we haven't been involved in any of those buildings. We started Transsolar 20 years ago, and we started it by doing computer modeling. I think that was the ability we had. We were capable of running sophisticated modeling tools. I don't want to go in detail what I show here, but this is a result of thermal modeling. Here, a geothermal system showing the temperature in the underground, some fluid dynamic modeling, some daylight modeling. And what we didn't know is, like, architects were very surprised that all of a sudden there was some scientific supporting the design process. And I think we were one of few firms, and I think there are more firms than just Transsolar, but one of few firms who use these modeling tools as design tools in the design process. So a lot of modeling is done when the design is finished, which we feel is not useful at all. If it's not interactive, integrated into the design process, it's not very useful. And we did this, and so therefore we started to become a partner in the design process without considering ourselves being architects. We still consider ourselves being engineers. Oh, but what's the task? I think, what are we facing? Basically, we have to get our completely building stock to become carbon neutral. I think that's the task we face for the next 40-ish years, let's say. And just to give you some evidence for this, the European Union established what they call the European Union Carbon Roadmap 2050, which states that carbon emission has to be reduced by 80% until 2050, and the building stock has to come down by 90%. So 10%, because it was considered easier to reduce carbon emissions from building than you're reducing carbon emissions from manufacturing, from industry, or from traffic. So that's why the task is even bigger on the building industry. This is the task that I think we are facing, and the question is, like, what can we do to create better environments using less resources, having less carbon emissions? What we see recently in all this sustainability hype we are facing is something where people apply gadgets to something which is stupid to begin with. And what we are always interested in, the question, like, how can we create efficiency by design? So how can we integrate design efficiency into the architecture approach? Now, a building needs to be more than just a racing boat. A building doesn't need to swim, and it doesn't need to be fast, and it's facing more forces than just being efficient. So the aesthetics is certainly going to be different, but it's this kind of thinking that has to go into the design process. Just going back a little bit, this is the Flatiron Building, Manhattan Flatiron Building, built in 1902. What you see is every single window has external shading. Every single window is operable for natural ventilation. And there was a very simple reason. Carrier invented air conditioning in the 20s. So none of those buildings had air conditioning at the time, and the designers knew exactly like how they need to build a building to make the best out of the situation. Now, Manhattan can be nasty. Manhattan is not Santa Monica. It can be hot and humid. And I don't want to say it was always great, but it was the best they could do, and it worked probably 90% of the year. It worked very well. Now, over the course of 80 years, all of a sudden, buildings look like this, and no operable windows, so much coating to deal with the solar gains in this building, so that environmental quality became even worse, and energy efficiency became worse. And what's amazing is when there's a power outage in New York City, people have to leave this building because they can't open a window. There's no access to light and air, whereas people can still stay in the Flatiron Building built 80 years earlier. So something went obviously wrong, and the question is not should we go back to the Flatiron Building, doing only Flatiron buildings. The question is, like, how can we become smart and integrate this thinking into contemporary design? This is a building I show later. It's a double facade building in Canada, where we use the double facade to provide controlled natural ventilation. This is a building we work with Danish architects in Hamburg, where we first time used the single layer ETFE facade to create this buffer zone, which allows people to have natural ventilation. And this is in a very odd situation because there's the cruise ship terminal basically a block away from this building. And when these big cruise ships are in the harbor of Hamburg, they basically have smog conditions and people can't open a window. And what we did is we connected this space here, we connected to the courtyard of the building so that the fresh air is integrated by the courtyard and people can still open the window and have natural ventilation, and also the shading is protected against the wind they have in Hamburg. But what you see is, like, this is a measure which has a big impact on the performance of the building, but also on the quality for the people. People can have natural ventilation whenever they like, and it's not something you can solve with a smart machine which is going somewhere into the basement. It's part of the design. So that's why we still believe that design is the key for better buildings, for better environments. Now, there's a trend right now which they call architectural thermodynamics. A lot of talking about architectural thermodynamics at the GSD. We feel like it's still climate engineering. I think this is would be the term we use. But it's about understanding all these physical effects and how they can influence design and how we can integrate it into the design process. Just to give you one example about what we call the visualization of climate engineering was a cloud we did at the Architecture Biennale in Venice. In 2010, we got asked by Sejima to do an installation there. After a while, we discussed, like, usually what we do is invisible, so what should we show there? And so we came up with the idea of a cloud. Because a cloud is, let's say, as I said, it's the visualization of climate engineering. And the cloud, the principle of a cloud is you need to have a saturated layer of air with 100% humidity, and then you can spray in water, and it doesn't evaporate because it's saturated already. And because if it would evaporate, it would cool down and would drop down and create a fog, which is on the floor. So this layer of warm, humid air is lighter than this layer, so it floats on top of this layer. But as soon as the saturated air is touching the ceiling, you get condensation on the ceiling, and then the cloud is gone immediately. So you need another dry and hard layer on top of it, which is squeezing the cloud in between to make it float. So this is the physics, and it's fairly simple. It took us, I would say, something like 4 months of testing until we got the stable layers of air in this space at the Arsenale. Tetsuo Kondo, an architect from Japan, he designed the space, and he designed the ramp where people could walk through the cloud layer and experience what it means to be in 40 degrees, which is 100 Fahrenheit, 100% humidity, which is pretty uncomfortable, I have to say. So this was the cloud from the top of the ramp, and people could really experience the various temperatures and humidity layers, and also get a sense of adaptive comfort, because all the sun coming down was always comfortable, no matter how hot it was in Venice. So another project, we worked with Achim Menges from the University of Stuttgart, running the Institute for Computational Design. It was for an installation at the Centre Pompidou. And Achim, he developed and invented this idea of this hygroscopic, let's say, sculptures or morphology where, like, timber bends dependent on humidity of the space. Just to simplify it a little bit. This was testing. Like here you see, like, low humidity, and it's all closed, and then if humidity goes up, the thing opens. And then this is a whole installation already, testing different humidity levels, and there was a long period of testing done at the university in Stuttgart before the big box was built and shipped to Paris. Now we designed the climate in the space like a very simple, relatively simple task compared to everything else. But the idea was that we show like a week typical outdoor humidity conditions in Paris. So we looked for a very typical week and display it in a box, which is then inside the Centre Pompidou. And then, like, the installation opens and closes independent of this artificial outdoor humidity level they would have in Paris if the Centre Pompidou would not be fully conditioned. Which is a little odd because, like, here you see that this is all the piping required to create constant conditions inside. And this is the piping we needed to reverse it. To create outdoor conditions in this box. It's a little weird, but it worked out fine. So this was the final installation, and you see all these, like the entire morphology, the entire installation, and it opened up. I have this video which illustrated much better. Like this was just one piece when it was closed and one piece when it was open. Let me show you the video. Like this was done at the Institute for Computational Design in Stuttgart, Achim's Institute. Again, we were only supportive on the climate for this installation, which became, I think it's going to become a permanent installation. I think it's very interesting that he's using wood as a composite material, like this very traditional material, and giving it this high-tech function. But it's also interesting the question, like, how could we use it to control climate in a space naturally without any mechanical systems, without any building management, building control systems, sensors. It's just the sensor and the operation, everything is part of the material. So, getting a little bigger than this, I thought I'm going to show this one, which was a competition we did with Greg in Italy, in the Trentino, which was a spa and an upgrade, an energy upgrade for an existing building, which is here, which we covered with a new facade. And then there was this idea of this spa, and like in the beginning, we had this discussion with Greg of how we should organize the program for this spa. And we did this very simplified diagram, which became a little bit the driver. And it shows like the same idea of the cloud, like how could we layer temperature and humidity to make it so that it makes spatially sense, and like warm air and humid air goes up. So we have the swimming pools at the bottom, and then like, I'm not sure what the different spaces had been at the time, then the sauna, and then the hot sauna on the top, so that it really, the temperature is part of the overall organization, the temperature and humidity, the thermodynamics, and it's starting to create this vertical spa, which became the driver. And here you see how everything came together and functioned so that we can operate it in Italy, very mild climate, that can operate it naturally and providing daylight. And here a final rendering. And unfortunately, we lost this competition for whatever reason. I think we all love Italy. That's why we always tend to do competitions in Italy. Most of them tend to become a mess at the end. Often you don't even get a result of the competition, but at least we have a reason to go there, get some dinner. On something similar, we're working with Philippe Ram and Katrin Mosbach, a landscape architect from Paris, and Philippe Ram, an architect from Paris, on a park in Taiwan where he won the competition, or they won the competition, with applying devices into a huge park in Taichung. It's called the Gateway Park, with the idea to manipulate locally the climate in the park. Like usually people in Taiwan, they don't go into a park, or not as much, because like it's too humid, like they have a lot of pollution, so it's not as comfortable to be outside as we are used to it. So the idea was, how can we use very simplified or simple technologies to upgrade the conditions in the park and to create better environments so that people can spend time there even in the course of the summer. So we analyzed the climate, and like this is the outdoor temperature, this is temperature and humidity, and like if you go to the right it's getting too warm, if you go up it's getting too humid. So this is the area where it's too humid, this is the area where it's too hot, and there's not much remaining. So then after we analyzed also the wind, we looked at where does the wind come from, where does the wind come from during the day, during the night, the hard wind, the humid wind, etc. We started to do some CFD modeling for the whole park to see where we have high airspeed, high velocity, so that we use the wind to improve thermal comfort by creating air movement. And we also did some solar exposure study to indicate where we have the highest solar exposure, where we need more shading, etc. So after that, like we started to map the whole park for pollution. There are a couple of streets, heavy traffic streets surrounding the park, for humidity and for temperature, and then combining all of those and then applying all the devices all over the park where they are most appropriate. So that we started to really program the whole park to create zones of low humidity, low temperature, or low pollution. And like various times a year, there's also a bigger solar facility, a big solar plant, which operates all these devices so that it's all carbon neutral, zero energy. And it's still in process of design. So this was everything in the category what I would call the thermodynamic architectural approach, or let's say, we would say, how can we use climate engineering to support creating better environments? Let me show you a building we did in Winnipeg, in Canada, where we worked with KPMG architects from Toronto. It's for Manitoba Hydro. It's the utility company there. And you wonder, like, they had their really high ambition. They wanted to have the most energy efficient high-rise building in North America. And you wonder, why does a utility company want to have such an energy efficient building? And if you look a little deeper, you find out that utility companies in Canada are still not private. Like, there are crown corporations, they call it in Canada. And the local provincial parliament, they basically dictate the rate they can sell their power to the people. But as soon everything which is left over, they have 90% hydropower, everything left over they sell into the United States. And they sell into the United States on a higher price than what they can get from their own people. So that's why they are so ambitious on convincing their people to save as much energy as they can. And not only that, they also, since they have so much hydropower, they buy power from the United States at nighttime on a very low price, pump up their lakes, and sell it back during peak times the next day. And when we worked on this, they designed a new dam for $4 billion, so it must be a very profitable business. So that was the reason why this needed to be so super energy efficient. So we started to analyze the climate, and unlike Taiwan, it's basically the opposite. It's freezing cold there. They have, like, almost half the year, they have temperatures below freezing. Like, this is freezing. And then it goes down to minus 30, which is about the same in Fahrenheit and Celsius. And over a period of 2 months, they have temperatures of minus 30, and then in summer, it's getting hot, like temperatures of 90 plus, and humid. So, and then they have strong winds up there in the prairie. So when we started to work there, we thought, oh my God, like, I got there for the interview in January, mid-January, and I got out of the airport, and I thought I'm going to get a glass right away. And I jumped on a cab, and I said, oh my God, this is cold. And then the cab driver said to me, oh, we just got a heat wave. Then you know how cold it is. But then everybody said, whenever it's cold, it's always sunny. So we started to look at how much solar radiation do we get on a vertical south facade. And this is shown here, like the 12-month. And we started to, blue is Winnipeg, we started to compare it to the absolute maximum, which would be every day, no clouds. Like sunny every day. And you see, like, there are months, like March, where we reach almost like 80% of the maximum. And then we compared it also to Toronto, because Toronto is considered a mild climate in Canada. So this is how minus 35 feels like. It's like boiling air thrown into the air, freezing immediately. A lot of the discussion, because it's a crown corporation, as I said, they're making tons of money by selling power to the Americans. But at the same time, they need to justify all their investments in front of the public. So it was always a big debate of, like, how much they can really justify it and what's reasonable. And we found these simple diagrams which show increase in productivity based on environmental conditions. Like, this is a building where they had daylight and reported something like a 15% increase in productivity compared to their old facility. Or this is a building where they have individual control over their ventilation, which we say this is nothing else than an operable window, which is again something like 10% increase in productivity. These numbers are enormous. It's like there is this rule of the thumb that if energy is $1 a square foot, then the building is $10 a square foot. The staff working in the building is $100 a square foot. So if you can increase productivity by 1%, it's as much as you pay for the whole energy used in the building. If you can increase it by 10%, it's as much as you pay for the whole building. So this is why this is like a big deal. if you can really increase productivity. And we started, or Manitoba Hydro started to put a number, a very conservative number, they use 2%, into their balance, into their financial balance. And all of a sudden, this freed up a lot. So there was no design competition, so they required various design approaches from the design team. And we tested all of them and many more for energy, for urban issues, for environmental issues in the surrounding, etc. And then highlighted those 3. And finally, this one became the best. So we ended up with this scheme of like almost like a twin tower in this capital A form, where this bar is facing east, this one is facing west, and due to the shape, we gained this due south facing winter garden, which became basically the lung of the building using all this passive solar energy. So here, this is a cross-section going through the building. The building has a 3-story podium and then 3 6-story, we call them neighborhoods. And there are always these 6-story winter gardens with a water feature inside, which is used in winter for humidification. So in winter, we get the outside air, we get in through this winter garden. We heat it up, we distribute it by a raised floor plenum into the depth of the floor plate, and then get it down where we have a heat recovery unit, take the heat, put it on water so that we get it back to the supplier unit. And then in addition, we have some tubing in the superstructure so that the superstructure itself provides heating, radiant heating for the building. And then in summer, when we don't need heat recovery, we exhaust naturally from the building. And then on top, we have something like 300 boreholes under the building, each one going down 400 feet for a geothermal heat exchange. And this geothermal heat exchanger is providing something like 50% of the heating load and 100% of the cooling load. Now this is this south-facing winter garden. This is where we have all the air intake units, providing the fresh air by this bench into this space. And then the water feature is where the picture has been made of. And then the units which take the air from the space and supply it into the floor plate are behind those panels. So this is basically the mechanical room of the building. Like, despite the boiler room on top of the building and some electrical rooms in the basement, there is no mechanical room in the building. This is it. And then having these interconnecting stairs to encourage people using less elevators, etc. Now, this is the same winter garden in the podium. Here at the backside, you see the water feature. You can barely see it, but they like it so much so that they even use it for the yoga classes. And this is where we collect all the exhaust air, which is at the north end of the building, getting the exhaust air into the solar chimney here. So there's no horizontal ductwork in this building. We supply by the raised floor plenum, and the air is traveling under the ceiling towards this chimney. And then to the east and to the west, we do have a double facade. And what the double facade is doing is basically providing weather protection for the shading, which runs in between here. But then also it allows people to have operable windows in here so that they can have natural ventilation whenever they want. Like, this is the mechanical ventilation, this is the radiant tubing. And like, we monitor the building since it's finished, since it's occupied for something like 2 or 3 years. And last year they operated this building almost 40% of the time in natural ventilation mode. Like, when they go in natural ventilation mode, they turn off all mechanical systems, so then there's no air coming from the raised floor system, from the raised floor. Like, 40% is enormous in a climate where there are basically no intermediate seasons. Like, it's either cold or hot in Munich. There's almost nothing in between. And like, this is the exterior facade where we control the natural ventilation. What was important for us when we proposed this natural ventilation, everybody was scared to death. There's literally no commercial building in Winnipeg which has operable windows. It's not Los Angeles there, from a climate perspective. And people said to us, operable windows, that's a maintenance nightmare. People open the windows when the seals are frozen and the seals break, and it's a nightmare. So by doing this double facade, and we control the windows to the outside. They are all motorized. Then all of a sudden, there's no risk that the windows inside can freeze. And it was basically the only possibility to convince the client of having natural ventilation. But what was most important to us as well, or also important to us as well, was that to get the shade outside the conditioned environment. By doing this, we can operate this building based on this radiant system, having 100% outside air we supply to the space. No recirculating air. And whenever we get there, the biggest compliment we get from an environmental perspective is the air quality. People recognize this. And I have to say, the air quality in buildings in this super cold climate, as well as in this super hot and humid climate, if you go to Florida, air quality is a big issue. Like, you get into the space, you smell it, you feel it right away. And people say if they have a lot of people on their staff with respiratory issues, they say they have no problems since they're working in this building. So from an energy perspective, like if we compare this building to others, these are all Canadian buildings. These are new Canadian buildings. This is like Canadian Energy Code when we built this building. And this was an incentive program from Canada for energy efficient building design. And this is what this building was designed for. And after 2 years of monitoring, you see we had some issues in the beginning. So this is the first year where we had a full year of operation. In September of 2010, we are looking back for 1 year, and then it's rolling. Then in October 2010, the previous year, etc. Well, you see we had some issues with the hydronics, which got fixed here. But it took us almost 2 years to get the building to what we have predicted. And I think it's a little long, was also because of this hydronic issue. But as a matter of fact, I think I've never seen any building which just works as designed. I think every building needs some fine-tuning in operation, and it takes a winter and a summer season to get it fine-tuned. But then we usually get it to what we have modeled, or we always get it there. But let's say we also looked at what does this building do to the local environment, and we did this wind modeling right at the beginning, and you see that there is a component which is going down. So we're like, when wind hits a building, it always goes in all directions around this building, and there's always one component which is going down. We try to make it more aerodynamic. You can't solve it with the shape of the building. It's just simply impossible. Like, you can reduce it, but you can't solve it. There's always this component of going down, and at the end it was this simple canopy, which was the solution, which basically redirects this downdraft before it hits the pedestrian level, and redirects it straight to the neighbor, because like he can't open his window anyway. It doesn't matter that much to him. No, but it's really important, and there are areas in New York City, Toronto has big issues with downdraft too. Like, it's an issue of cold climates, it's not an issue of Los Angeles. But there are areas in New York City where they have to close off the sidewalk in winter when they have snow, because the downdraft is so strong that they can, let's say, it becomes too slippery for people. And then the other thing was shading. There's the Air Canada Plaza, and the idea was that we do not shade Air Canada Plaza in summer. And like in these various schemes we have developed, the board at the end always wanted to have this tower, because this tower was, because it's so narrow, it would have become the tallest tower in Winnipeg. And all of a sudden, like, they have all these high ambitions of energy efficiency and environmental quality, but all of a sudden issues like tall are becoming more important. Which was convincing at the end that this scheme, which was most energy efficient, didn't cast shade on Air Canada Plaza in summer. So that was the convincing argument at the end of the day. So then what we did, we extended the solar chimney to make it still the tallest building. So this is the canopy that deals with the downdraft. And it has a depth of something like 6 or 7 meters. So it really needs to be massive. Like, you can't do something which has a meter, or like a couple of feet. It needs to be like 6 meters, something like 20 feet. It needs to be massive to really deal with all this wind which is coming down such a big building. What was also interesting is this was the fact that they have all their facilities in the suburbs so far. And the fact that they moved downtown was reinforced by the former mayor. And part of the deal was that everything they find in the surrounding, so the idea was using this building to revitalize downtown Winnipeg, like a dying mid-sized prairie city, and getting 2,000 people downtown was a big deal for the city. So whatever they found in the surrounding, in terms of business, they didn't build in the building. The building has no staff cafeteria. The people have to go into the city for getting lunch. The building also do not have parking. People have to use public parking garage. And so what happened is, they did this statistic just recently, whereas in the suburban office, only 10% of the people come by public transportation, carpool or cycle. 90% come with their private car. And this is the downtown office now, 84% come with public transportation, carpool or cycle. And only 16% come with their private car. And like the sick days reduced by 1.25 days per person a year. We did a brief calculation. The energy savings are something like $800,000 a year. The savings just by these 1.25 less sick days are something like $2 million per year. And this does not take into account the productivity when people are actually sitting in the space. So here you see the extended solar chimneys to make it this tallest building. Like physically, up to here would have been sufficient. And then another building I want to show you, which is the one that is on your website, is the Novartis campus building where we worked with Frank Gehry. And in the beginning, we developed this scheme, like a house-in-house approach. So there are these office areas which are basically separated from this buffer zone, and we supply, similar to Winnipeg, we supply air into this, into the office space, and it kind of extends into the buffer zone and used to condition, like the exhaust air is used to condition the buffer zone. What was interesting is that we covered the shell with photovoltaic, with transparent photovoltaic, and therefore we did the solar exposure study to find out where is it worthwhile to put in both photovoltaic and where it probably doesn't make any sense. What was interesting is that we calculated that because of this house-in-house approach and the buffer zone, so that we don't need to fully condition this envelope or the space behind the envelope, and we use the exhaust air to condition it, plus the photovoltaic, per square meter or per square foot shell, we gain more energy than we lose. Which is quite interesting because so far the paradigm was you have to minimize surface and your envelope to become more energy efficient. All of a sudden it's reversed, like you can maximize your envelope and you're still better. Again, in this combination. And like this is how it looks like. And you see it's still transparent, like when you're inside you still see the clouds. So what they did is basically they put the PV onto the glass, and then with a laser they cut lines off to make it almost like a fritting, so that people can still look through it and you get daylight through it. And this is from the inside. Here you see the clouds moving by. But again, I think what was really interesting is this shift in paradigm, that you gain more energy than what you lose by the surface. And another very recent project which is still under design, is this building, this lab building, where we work with Danish architect in Lausanne. And what is interesting for us is that we use this fixed grid as a shading, as fixed shading for the building. And here you see how it works. Like this is the write-up space, and having natural ventilation, having radiant heating and cooling. It's like the typical suspect equipment. And then this is a rendering from the inside looking through this shading device, through this grid. So what was interesting for us is that we said, let's try to use, let's say, smart parameter tools to optimize the shading system. And we used Grasshopper, we tested Grasshopper in combination with thermal modeling for a while. But this was the first time where we linked thermal modeling as well as daylight modeling to Grasshopper in order to optimize this structure. And like, it's a pretty bad movie. We have some movies which are worse. So. So this is the final result. So what you see here is like daylight autonomy, heating demand, cooling demand, lighting demand, and then everything combined in the primary energy required for operation. So what happens is we move one corner of the grid up and down, and you see how daylight goes deeper into the space. Why does it come on? So daylight goes deeper into the space, but as daylight goes deeper into the space, all of a sudden the cooling loads go up, and it all runs very fast. I think we should put it. So, and then as it gets more close, the daylight is getting worse again, but then the cooling loads come down, the lighting loads go up. So it was really useful tool for us to see how the parameters really combine and, let's say, what's their impact on the environmental quality in the space, but also the overall energy performance of the space, and how does it all come together in one model. It's one coherent model which we could use to test it and to optimize it. It's very simplified, it's a very simple task. Like, it's just a grid, and we take one corner of the grid and move it up and down, left or right, and see where is the optimum, and then we could do the same thing. Like, go back. Like for each orientation, like each slope, each orientation, we could do the same thing, very simple, and really optimize it. However, like, this is, in my mind, this is just the beginning of how we could use parametric design to really optimize buildings. And it's very rudimentary, it's just a shading grid. Before we started to optimize skylights with parametric design, a lot of it is still in a stage where if you look deeply onto it, you come to the same result than the computer does. But the question is, like, can we enhance it to a point where the results start to become, let's say, unexpected and unpredictable? I think that's the main question. And we're still not there, I think. I think there's still a long way to go, but it's starting to make sense also in projects to integrate it in project design, not just for testing purposes. So finally, I want to show you the last one, which is a very simple building we did, but a very nice one in Damascus, the French school where we work with Atelier Lyon architects from Paris. And I really like to show this because, like, these Manitoba Hydro buildings or the Novartis buildings are all these corporate kind of firms where they put a lot of money onto it to showcase their power. And this was the opposite. It was like a parents association came and said, like, we want to have a building, can you do a building without air conditioning? Because we feel like air conditioning is making our kids sick. This is what they told us. And it's probably true because, like, the air conditioning systems are not maintained. So you don't want to see what the air quality is, which you get out of these systems. So for us, we used it as a challenge. At the same time, it needed to be a super low budget building, 100% paid by the Parents Association. The French government, they paid for the land, they paid for our fees and the architecture fees, but not for the construction. So we ended up with these two-story classroom buildings with this, with this courtyard in between. And then there's the shading and the vegetation to kind of create a nice microclimate in between these classroom buildings. And And then we take the air from the courtyard and we draw it through pipes which are embedded in the ground slab and distribute it to the space. And then it's going out this solar chimney. And then there are more pipes which are connected to the upper classroom and also going out by the solar chimney. The solar chimney is like facing west to catch the low sun angles before sunset. And it has some polycarbonate on the west facade. And on the back side, it's a masonry wall painted black. And so the sun heats up this wall, and the wall absorbs the heat and keeps it warm so that it keeps this natural ventilation running even at nighttime. So there is no fan in the building, there is no motorized flat, there is no building control system, there is no nothing. The kids are responsible to operate it, to open the flaps for natural ventilation. If they don't open it, they get 100 degrees in the space the next day. So they learn pretty quickly how to operate it. And we in our modeling, we showed that we still get, in a hot period, like in June, they have 40 degrees every day. But the beauty is that it cools down at nighttime to something like 70 degrees every day. So that's why the night ventilation is most important, so that we cool down the thermal mass of the building to keep it cool the next day. But we showed them in our modeling that at the end of a hot June period, at the end of the day, they get temperatures up to 90 degrees or 85 degrees in these classrooms. But the parents came and said 85 is fine if we have 100 outside. And so they operated, before the Civil War, they actually wanted to extend the school with the same principle. When we worked on it, we had an engineer, a mechanical engineer from Beirut. He said to us, I don't care what you guys are doing. Like, as soon as you're gone, I'm going to put in split units anyway. So there's still no split units in this building. Here, this is a nighttime picture. I like to show this because, like, this is not this fancy type of corporate facility. This is very down to earth, and like something I think we really need to think about in our practice every day is like, how can we really simplify things? The biggest problems, when we have problems in our buildings, we never ever had an issue where we had done a wrong modeling or where we had not considered the physics correctly. Never ever. But we had tons of issues where the controls didn't work, and sometimes never worked. So sometimes I say, like, we need to design buildings which don't need any controls. I think it's kind of ridiculous that in a car we can break individual tires within milliseconds, but in a building it's too much to open a window if the space is getting too warm. So you think like it's a kind of a different century we are in the building industry, but that's the truth. So I think the less controls, the better. The more resilient the buildings are, the more resilient the design is. And I also think it's a kind of weird that people are used to operate their house at home. They open the window, they close the shutters, etc. But as soon as people get into a commercial building, they feel like everything needs to be taken care of. And I think it's wrong. And I think it's important that, in this case, kids getting used to interact with the environment, to interact their building with the environment. Let me finish with this picture. It's a spa in Tokyo. And we found this in a magazine. Hitoshi, I'm not sure if you know this spa. Probably not. There are probably many spas in Tokyo. Yeah, but what we really liked is the advertisement they had where they said, welcome to breathtaking Tokyo water park. And then they said, where you can wash away the pressure and stress of the overcrowded city. But what I really like about this is, like, I have no idea how much energy they use, but the energy consumption per person is certainly negligible. And I think this is something we always have to keep in mind. Like, we do buildings for people, and if people don't use it, it's a waste of resources, no matter how efficient it is. In this spa, no matter how efficient or inefficient it is, it's by definition efficient with regard to the people using it. So, like, sustainability can never be something you can give to an engineer to solve it. It's integral part of the architectural approach, and the design is at least as important, because if people don't like the building, people don't use it, and then it's a waste. So that's why, let's say, I think it's a holistic requirement, and it's not something you can hand off. It's something which you guys will, let's say, probably have a big impact on your whole professional career. Thank you very much.
For those of you who have questions, Thomas will stay and you can talk after.
Actually, Richard, I wanted to ask one question which I think will be relevant.
Okay.
So at a body that everyone can
I want to ask one question because we have a room full of students, and there are some things that really like to comment on. Because I think you're preaching to the choir in many ways, but the mechanical engineering profession in the United States looks at many of these issues we talked about as unreliable and things that will, and I'm always fighting them. So, but they would not allow indoor temperatures to go to 85 because it's against their professional standards. And they would also not allow many of the other things, and we're in a constant friction with the mechanical engineering establishment. So could you comment on how these issues might be?
Let's say, first of all, it's not an American issue. I think it's a global problem. It's a global problem that mechanical engineers, and I don't want to say that they are not good. I mean, that's not the point. That they get sued for, or they fear to get sued if they don't provide what they consider the ideal, whatever the ideal is. And that's what's written in ASHRAE.
Yes.
I think, let's say, this is one thing which is really driving budget up, because what we end up in most of the buildings we are doing, is, particularly in North America, is that we have both. We have a mechanical system and we have a passive system. So that there is still, and it's not just the mechanical engineers, it's also clients. Clients in this country, especially corporate firms, are also institutional, like when you deal with facilities of universities, which we do a lot recently. They are scared to death if there is no switch where people can say, I want to have 72 degrees now. And the funny thing is that they are most scared about the faculty. They always use the faculty as an excuse. They always, like, you do not believe how often I heard the faculty would not accept this. And we always say, let us talk to the faculty. And this is something, you know, they are scared of some ideas, if we get them on the table with the faculty, they never get them off the table. So that's why they are so concerned. But it's yeah, I know, it's like, I think the only thing we can do, is to prove that we can provide better environments, better buildings, with less equipment. And I think what really helps us, there is in ASHRAE now something which is called adaptive comfort standards. And the school in Damascus would follow the adaptive comfort standards of ASHRAE. So it would not be against ASHRAE. The ASHRAE the ASHRAE handbook became pretty flexible. Just nobody is using it. I think that's the issue. The ASHRAE is, what does ASHRAE stand for?
Association Society of Heating and Engineers.
Yeah.
Something like that. Heating and air conditioning engineers.
Like, it's the Bible for every engineer. Everything is written in the ASHRAE handbook. Everything. What is comfortable, what is not comfortable. And again, but these adaptive comfort standards would actually provide us our flexibility we need, just nobody is using them. And then if you then confront clients and the mechanical engineers about it, say, let's use the adaptive comfort standards, then they come and say, faculty would never accept that. So it's a kind of trap. But I think, again, it's we always say, like, forget about codes, forget about standards. Let's think about what's the right thing and what's the best thing. And then we talk later how we get them into the code. I think we can only prove by example. Like buildings like Manitoba Hydro, we had an issue where we worked for a school in Chicago. We couldn't get facilities to visit the building in Winnipeg. It's a 1.5-hour flight time. It's not a big deal, and there's direct flight connections. We didn't get them to go there because they were scared of getting convinced. So we better not see it. Yeah.
In Europe, or especially in Germany, they're pushing a lot for passive houses, passive heated conditions, which is a controlled ventilation system. And your project, I mean, going the other way, essentially.
Yeah.
More ventilation outside of the Is this, I mean, and also there's the architects complain because there are not enough windows. So is there a way that this sort of, because of the saving energy issue, this model has become so popular, or is getting pushed as a model for building stock in Germany?
Yeah, I think it's kind of a weird process right now. I have to say I'm not a big fan of passive house for obvious reasons, and I think they proved that the buildings become very energy efficient, but you're basically like in a warehouse. You're in a sealed box, you minimize fenestration ratio, and you're living off a mechanical unit, which gives you life. And I think the name passive house is very misleading. It's basically an active house, because you need an active system to survive in this building. But they proved that they can operate very efficient. What I don't like is to make such a dogma out of it. I think what we need is more than one model. I think we need to have choices. People want to live in a passive house, fine. But if people want to live differently, there needs to be another model. And at the end, what counts is the result and not how you get there. And this is what we always fight it against, that people give you distinct guidance of how you get to your result. I think it's just the result that counts, that should count. But it's there's people started now the active house movement as a counter to the passive house. It's all bullshit.
The active user house.
Yeah, exactly. And the smart user house, smart city, and the smart grid. Okay. Thank you very much.